understand the simple concept of combinations using an example. Assume that there is a group of 3 lawn tennis players X, Y, and Z. A team consisting of 2 players has to be formed. Note that here order is not important. There are 3 possible ways in which the team could be constructed. The first group of X and Y, the second of Y and Z, and the third of X and Z can be formed. Therefore, the possible groups are XY, YZ, and ZX. Here, each selection is called a combination of 3 different objects taken 2 at a time. Now, we obtain the formula for finding the number of combinations of n different objects taken r at a time, denoted by NCR. Corresponding to each combination in the list, the players can be rearranged in 2 factorial ways. Hence, the number of permutations equals 3c2 into 2 factorial. On the other hand, the number of permutations of 3 different players taken 2 at a time is 3p2. Therefore, 3p2 is equal to 3c2 into 2 factorial, or 3c2 is equal to 3 factorial by 1 factorial into 2 factorial. Theorem 1. NPR equals NCR into R factorial, where R is greater than 0 and less than equal to n. Let's see the proof of this. Corresponding to each combination of NCR, we have R factorial permutations. Because R objects in every combination can be rearranged in R factorial ways. Hence, the total number of permutations of n different things taken R at a time is NCR into R factorial. On the other hand, it is NPR. Thus, NPR is equal to NCR into R factorial, where R is greater than 0 and less than equal to n, or n factorial divided by n minus R factorial equals NCR into R factorial. Therefore, NCR can be written as n factorial divided by R factorial into n minus R factorial. Theorem 2. NCR plus NCR minus 1 equals n plus 1 CR. Now this is a very simple but a important relation which is very useful for solving problems. Come, let's learn it nicely. Writing NCR plus NCR minus 1 in its factorial notation, we get n factorial divided by R factorial into n minus R factorial plus n factorial divided by R minus 1 factorial into n minus R plus 1 factorial. Now in the first term, we break R factorial into R minus 1 factorial, and in the second term, we break n minus R plus 1 factorial as n minus R plus 1 into n minus R factorial. Now further, taking n factorial divided by R minus 1 factorial into n minus R factorial common and then simplifying it further, we get n factorial divided by R minus 1 factorial into n minus R factorial into n minus R plus 1 plus R divided by R into n minus R plus 1, which can be written as n plus 1 factorial divided by R factorial into n plus 1 plus R, which can be written as n plus 1 CR. Always remember, NC n minus R is equal to n factorial divided by n minus R factorial into n minus R factorial, which is equal to n factorial divided by n minus R factorial into R factorial. That comes out to be NCR. Therefore, NCn minus r is equal to NCr. So in words we can say it as selecting r objects out of n objects is the same as rejecting n minus r objects. Let's learn the proof of 0 factorial equals to 1. We have NCr equals to n factorial divided by n minus r factorial into r factorial. For r equals to n, NCn equals to n factorial divided by n minus n factorial into n factorial, which is equal to 1 divided by 0 factorial. Now, NCr can also be written as NPR divided by r factorial. For r equals to n, NCn equals NPN divided by n factorial, which is equal to n factorial divided by n factorial. It cancels out to be equal to 1. Therefore, 0 factorial is equal to 1, which is proved. Now remark, we can prove 0 factorial equals to 1 in the other way round as well, that is the logical way. Selecting nothing at all is the same as leaving behind all the objects, and we know that there is only one way of doing so. Hence, NC0 is equal to 1. Let's have an example. If NC9 equals NC8, then find NC17. Now the solution, we have NC9 equals NC8. Writing it in the factorial notation, we get n factorial divided by 9 factorial into n minus 9 factorial, which is equal to n factorial divided by 8 factorial into n minus 8 factorial. Cancelling out the common term n factorial from both sides and then rearranging the terms, we get 8 factorial divided by 9 factorial equals n minus 9 factorial divided by n minus 8 factorial. On simplifying it further, we get 1 by 9 equals 1 by n minus 8. Now solving this equation, n comes out to be equal to 17. Therefore, 17C17 equals to 1, which is the required answer. Let's have an example. What is the number of ways of choosing 4 cards from a pack of 52 playing cards? In how many of these 4 cards are of the same suit? 4 cards belong to 4 different suits. The 4 cards are face cards. 2 are red cards and 2 are black cards. The 4 cards are of the same color. Let's see the solution of all these questions. There will be as many ways of choosing 4 cards from 52 cards as there are combinations of 52 different things taken 4 at a time. The required number of ways is equal to 52C4, that is 52 factorial divided by 4 factorial into 48 factorial, which equals 49 into 50 into 51 into 52 divided by 2 into 3 into 4. It comes out to be 270725. Now, the answer of the first question is, there are 4 suits: diamond, club, spade, heart, and there are 13 cards of each suit. Therefore, there are 13C4 ways of choosing 4 diamonds. Similarly, there are 13C4 ways of choosing 4 clubs, 13C4 ways of choosing 4 spades, and 13C4 ways of choosing 4 hearts. Therefore, the required number of ways will be obtained by adding 13C4 4 times, which is equal to 4 into 13 factorial divided by 4 factorial into 9 factorial, which is equal to 2860. The answer to the second part. There are 13 cards in each suit. Therefore, there are 13 C1 ways of choosing one card from 13 cards of diamond. Again, 13 C1 ways of choosing one card from 13 cards of heart. Similarly, 13 cards of clubs can be chosen in 13 C1 ways. And again, one card from 13 cards of spades can be chosen in 13 C1 ways. Hence, by multiplication principle, the required number of ways are 13C1 into 13C1 into 13C1 into 13C1, which is equal to 13 raised to the power 4. There are 12 face cards and 4 are to be selected out of these 12 cards. Now this can be done in 12C4 ways. Therefore, the required number of ways is equal to 12 factorial divided by 4 factorial into 8 factorial, which is equal to 495, our required answer of the question 3. Now solving question 4. There are 26 red cards and 26 black cards. Therefore, the required number of ways is equal to 26C2 into 26C2, which is equal to 26 factorial divided by 2 factorial into 24 factorial whole square, which comes out to be 325 whole square, that is equal to 105625. Now the answer to the fifth part is 4 red cards can be selected out of 26 red cards in 26C4 ways, and 4 black cards can be selected out of 26 black cards in 26C4 ways. Therefore, the required number of ways is equal to 26C4 plus 26C4, which is equal to 2 into 26 factorial divided by 4 factorial into 22 factorial, which is equal to 29900.